Hello everyone, welcome to Veracious Academy. My name is Anil Kumar. I am an alumni of IIT Bombay. I have done my BTech from Mechanical Engineering. I have been teaching physics for the past decade for JEE Mains, JEE Advanced, Neet UG and other competitive exams. If you are interested to attend my sessions, please find the contact details in the description below. Let's get started with this lecture. Enjoy the video. First, we have yesterday's derivation. We had let the arc subtend an angle 2 alpha at the center, right? Right?
Yes, sir.
And let the wire has a charge per unit length lambda.
Yes, sir.
So the electric field, net electric field due to this wire at the center, at its own center, is in terms of lambda, we got it as 2k lambda sine alpha divided by r.
Yes, sir.
Now, if we want to get in terms of total charge that is present, then we substitute lambda is equal to charge per unit length, right?
Yes, sir.
But I told you that it is important to remember in terms of lambda because mostly questions can be solved using lambda easily. Okay.
Yes, sir.
So for quarter of a circle, so this is the general stuff. Now for quarter of a circle, we basically have only one side of it. So let this be lambda r. That means our 2 alpha is equal to 90 degree, right?
Yes, sir.
If we take quarter of a circle, this is our 2 alpha, which is 90 degree. Then my electric field at the center, resultant electric field, will be an angular bisector, by the way, right? It will be an angular
Yes,
bisector at the
Yes.
center, and it will be 2k lambda sine 45 degree, correct?
1/√. Yes, sir.
Divided by r, which is 1 by root 2. So basically, I will get k lambda into root 2 by r. So this I have to remember for a quarter of circle. I need to remember, right?
Yes, sir.
Now I'm not. Okay, we can do semicircle also because first I will show the application of usage of this quarter of a circle in terms of semicircle first, and then we can go to the 270 degree also. So yesterday we solved it using the sine alpha by alpha thing. That means the total
Yes, sir.
charge.
Yes, sir.
Right? Today I am showing you if we take it uh, 1/4 in terms of lambda, if we start calculating, then how it becomes easier. And then eventually, whatever is the question, we will eventually convert the lambda fellow in terms of whatever is given. Okay.
Yes, sir.
So those questions also we will solve today. So suppose I have a semicircle. Okay, semicircle. Now, what I am trying to say is that for semicircle, I can say that the angle 2 alpha is equal to 180 degree.
Yes, sir.
But instead of that, we can look at it like this also, that my semicircle is made of 2 quarters of a circles.
Yes, sir.
And this fellow will have k lambda root 2 by r as an angular bisector. This fellow will have k lambda root 2 by r.
Let we have to add.
Correct?
Yes, sir.
And these two will be at right angles with each other.
Hmm.
The angular bisector of this quarter and the angular bisector of this quarter will be at right angles with each other.
Yeah, sir.
Is this point clear, geometry?
Yes, sir.
Okay.
Yes, sir.
So, two vectors of equal magnitude A at right angles with each other will have a resultant of A root 2.
Yes, sir.
Two vectors E1 at right angles with each other. So the E net, I can write it as, if each of the electric field is E1, then this resultant will be E1 root 2 magnitude.
Yes, sir.
And this E1 itself is basically K lambda root 2 by R.
Yes, sir.
So root 2 into root 2 will become 2K lambda by R. Correct?
Here, can't we just add like K lambda root 2 by R plus K lambda root?
Two vectors at an angle 90 degree with each other. If they have in the same direction, I cap plus I cap is 2 I cap. But I cap plus j cap, I have to do vector addition, square root of a square plus b square.
Yes, sir.
Two vectors at an angle 90 degree with each other. Square root of e1 square plus e1 square, right?
Yes, sir.
Is this clear?
Yes, sir.
Now, in the 270 degree case, okay, so there are many ways to solve it. So, let me look at this method also. Okay, so
Semicircle plus quarter.
We have
I'm telling we can also solve by semicircle plus quarter.
let us see. Okay, so this is my circle.
Yes.
Semicircle plus a quarter, also you can think of it like that. Okay, or I have 3/4, right?
Yes, sir.
So this is my wire from here to here. That means this quarter is not available.
Yes, sir.
So, like you said, you can treat it as one semicircle and a quarter.
Yes, sir.
But if you look at the geometrical aspect of it, semicircle will have a resultant along this direction, correct? Here, semicircle will have a resultant along this direction. This is the resultant direction.
Yes, sir.
This remaining quarter of a circle will have along this direction, which is at 135 degree with each other.
Yes, sir.
Two vectors at an angle 135 degree, I have to do square root of a square plus b square plus 2ab cos theta.
Yes, sir. That will become
Lengthy. Or I can treat it as 3/4 of a circle.
Yes, sir.
Fine. I can treat it as 3/4 of a circle. The first quarter and the third quarter will anyways cancel each other.
Yes, sir.
And only due to the second quarter along its angular bisector, I will have the resultant.
Yes, sir.
And the net electric field, I can directly write it as K lambda root 2 by R.
Yes, sir.
Of course, my lambda over here, I mean, the total charge is 3/4 divided by, that's a different story. Suppose the total charge given on the entire wire is capital Q from here to here, right?
Yes, sir.
In that case, my lambda will be what? Lambda will be total charge divided by 3/4 of 2 by R, right? Is this clear?
Yes, sir.
3/4 of the entire perimeter. So yesterday we saw that we can substitute this and we got some 2 root 2 by 3 by R square. right?
Yes, sir.
Today we are only looking at the application of the lambda, why using lambda becomes more easy, right? This is the first way. I mean, I can cancel these two quarters, and the second method, which I was saying, which we discussed yesterday, is basically I still have 3/4 of a circle. Now, what I will do in this, in the place of the fourth quadrant, I will imagine a plus lambda and a minus lambda,
Yes, sir.
right?
Yes, sir.
So, for this, yesterday we discussed as two different scenarios. One is a full circle, plus the other is just the fourth quadrant having a minus lambda. Correct?
Yes, sir.
So, what is the statement that we say, which we have to get used to in future also is, in the question it is given 3 quadrants or 3/4 of the circle, 3/4 of the circle has a charge distribution, linear charge distribution. Find
Yes,
the
sir.
electric field at the center. So we will say add, it is given in the question that the lambda is given, okay, for the wire.
Yes, sir.
So what I will say, the statement will be add a wire having plus lambda in the fourth quarter also, and also add minus lambda at the same location, so that the resultant of it, addition and add plus lambda and then add minus lambda, eventually resultant will be you haven't added anything.
Yes, sir.
Why is that so? Because charge is conserved. What do I mean by charge is conserved? If at a point I have a charge of plus q, at a point if I have a charge plus q, and at the same point if I say I have a charge minus q, my total charge at that point can be treated as 0.
Yes, sir.
It will be 0. Correct?
Yes, sir.
At the fourth quarter, let me add a wire having a charge plus lambda per unit length and also minus lambda. So eventually, I will not have anything in the fourth quadrant, right?
Yes, sir.
And I can treat it as two separate situations. One having plus lambda everywhere and it becomes a full circle, and the electric field due to this is 0.
Yes, sir.
And the next one is only the quarter of the circle and having a charge per unit length of minus lambda, and the
Yes, sir.
electric field at the center due to this is the same as that quarter, but now it will be towards,
Derivation.
and the answer is basically magnitude is k lambda root 2 by r, only the direction is towards the wire, which is the same answer that we have over here, k lambda root 2 by r towards this direction.
Yes, sir.
So basically this way also we will get E ret is equal to k lambda root 2 by r. Is this clear?
Yes, sir.
I'll give you a question. Okay. You solve it first using this
Yes.
1/4 thing. So all the 4/4. So there is a thin wire. There is a thin wire, and all the 4/4 of the circle are charged, but they are charged with different lambdas. So take the charge per unit length in the first quarter as the lambda, second quarter as 2 lambda, third quarter as 3 lambda, and fourth quarter as 4 lambda. Find the magnitude of resultant electric field at the center. Okay.
Yes, sir.
Magnitude of resultant electric field at the center. Take a look. So let the electric field due to
Is it
lambda
3 minus 1, sir?
3 minus 1. Yeah.
I don't know why I wrote 2. Yes, sir.
Let the electric field due to lambda be E. Right?
Yes.
Then due to 2 lambda will become 2E.
Yes,
Due
sir.
to 3 lambda will become 3E. And due to 4 lambda will become 4E. Now 3E and E will cancel each other, and I will get 2E in this direction. Correct?
Yes, sir.
Similarly, 4E and 2E will cancel each other, and it will be 2E in this direction.
And now I'm getting 2k lambda. Resultants.
I understood. So, is this fine?
Yes, sir.
So, the resultant in terms of E is 2E root 2.
Yes, sir.
But so E net is equal to, I'll have it as 2E root 2. But what is E?
Yes, sir. K lambda root 2 by 2.
K lambda root 2 by R.
Yes, sir.
Right? Okay.
2, sir.
In the denominator, we have 2 or R?
It's I wrote it 2 from the notes.
So when you substitute this over here, you will get E net as 2 times K lambda root 2 by R times root 2.
Yes, sir.
Right?
Yes, sir.
The final answer will be 4K lambda
K lambda
by R. Hi guys, I hope you enjoyed this session. If you think this video was useful, don't forget to like, share and subscribe to my channel. Also, I'll be waiting for your comments in the comment section. See you in the next video.